All right, so this video is about pH, and pH is an expression of solution acidity, so it tells us how acidic a solution is. And if you remember maybe from Chem 1, all right, my stuff disappeared, here it is. This is a pH scale, so this is in your book. You can find it on page 676 if you're interested in looking at it. But basically, things toward the top are more acidic, things toward the bottom are more basic. What's in the center is neutral. So we consider a pH of 7 as neutral. If we are at a pH that is between essentially 0 and 6, we are going to call that acidic. If we are looking at a pH that is from 8 to 14, we are going to consider that basic. So pH in general ranges from 0 to 14. You can have negative pHs, not super negative, but you can have a negative pH if you have a concentrated acid. And likewise, you can have a pH for a base that's slightly above 14 if that base is concentrated. So for example, if you had hydrochloric acid that was 2.0 molar, you would get a pH for that would be a negative 0.30 molar. So anyway, so here's our pH scale. What I'm going to do now is I'm going to show you how we calculate all of these things up at the top. So I want to get out of here and I want to go back to Smart Notebook. So give me a second. Okay, so the first thing I want to do is I want to give you some equations that we're going to use for pH, and these ought to look familiar because hopefully you learned them in Chem 1. So the first one is pH equals the negative log of the hydrogen ion concentration. Now remember, depending on how we've written our reaction, this hydrogen ion concentration could also be a hydronium ion concentration because we kind of use them interchangeably. So either will work. Another equation is POH equals the negative log of the hydroxide ion concentration. And I'll do some examples showing you how we use each of these. Now, let's say you're given pH and you want to go back and you want to calculate the hydrogen ion concentration. You do 10 to the negative pH. And same thing here. This H plus could also be the hydronium ion. Thinking about bases the same way, if you want to find the hydroxide ion concentration, you're basically doing the anti-log, but because that log is negative, it's 10 to the negative POH. Now we can go back and forth between pH and POH by using another equation. So the pH plus the POH equals 14. And you can remember that if you think about the pH scale running from 0 to 14. And then we can also relate the hydrogen and hydroxide ion concentrations. So our Kw, which is called the ion product constant, is equal to 1 times 10 to the negative 14th. And that is equal to the hydrogen ion concentration or hydronium ion concentration. Either one, remember we're using those interchangeably, times the hydroxide ion concentration. And for right now, I think those are all of the equations I want to give you. So now what we're going to do is using these equations, and you'll find them all on your green equation sheet. They're all provided. I want to do some examples. Okay, so what we want to do here is we're given 6 different conditions. From these, we want to calculate pH, pOH, hydrogen ion concentration, or hydroxide ion concentration for these following solutions. And then we want to identify them as neutral, acidic, or basic. So what we're going to do is, let's start with A. And the first thing you want to notice is that you've got an acid. So you've got this hydrogen here. If you think back to stoichiometry, strong acid, so this completely dissociates. So what happens is we get 100% ions. So if this, let's make this easy. Let's say this concentration of HCl were 1 molar. And remember back in the fall, we said if the concentration of a strong acid or base were 1 molar, molar coefficients being the same, your hydrogen ion would be 1 molar and your chloride ion would be 1 molar. If this were 0.5, it's a 1-to-1 ratio, H plus would be 0.5, chloride would be 0.5. So now we've got a scary number instead of a nice whole number. So if hydrochloric acid's concentration is 6.7 times 10 to the negative 4th, then I know that that's also the concentration of H plus. So to find the pH, I'll do negative log of the hydrogen ion concentration, which is actually the concentration of that acid. So 6.7 times 10 to the negative 4th. So on my calculator, I'm going to hit negative Okay, so I'm going to do negative log of 6.7 times 10 to the negative 4th. And when I did that, I got, whoops, I need my pen again, 3.1739. Okay, now we have to talk about Sig Figs for pH, and this is not going to be fun. So you can do it one of 2 ways. You can do it the right way, or you can do it the way that will get you close most of the time, but not all of the time. So basically what you do is you look at the number of Sig Figs in your problem or your prompt. So there's 2 Sig Figs here. So what that tells you is after the decimal, you need 2 digits. So our pH would be 3.17. So once again, if you have 2 Sig Figs in the concentration, you're going to have 2 digits after the decimal for pH. And we'll keep reminding you of that, so you don't need to worry about that. Okay, so 3.17 is our pH for A. We need to identify pOH. So I can do this a whole bunch of different ways. We already know our H plus concentration, because that's what this is. So maybe I want to use kW here. So I'm going to say 1 times 10 to the negative 14th equals H plus concentration times hydroxide ion concentration. I want to get hydroxide ion concentration alone. So what I'm going to do is do 1.0 times 10 to the negative 14th divided by 6.7 times 10 to the negative 4th. And I get, Sig Figs are normal for this because we're not doing pH. I get 1.5 times 10 to the negative 11th. Because this is concentration, I need my units for molarity after that. Okay, so now we've got H plus We've got hydroxide. Now what I want to do, oh, we've got pH as well. I want to do POH. So because I calculated hydroxide ion concentration here, I can do POH equals negative log of 1.5 times 10 to the negative 11th. I will stick that into my calculator. And I get 10.82. I have two significant figures in my prompt, so because it's pH, I need 2 digits after the decimal. Okay, if I'm going to do B as an example now, and then I'm going to be done with this video and then create a new video for C and D and a new video for E and F. So if you feel like you've got it, you're done, you can stop watching this video and then go on to the next video where we start with bases. If you feel like you need to watch again, I am going to do B now. So first thing I do is I look at what I have. I have nitric acid, and here's my hydrogen, which is kind of showing me that I've got an acid. It is a strong acid. Whoa, sorry, I didn't mean to do that. It's a strong acid, so what that tells me is that nitric acid will completely dissociate. So that means I'm going to get all hydrogen ion and nitrate ion. The nitrate ion is not going to contribute to pH at all, so I'm going to ignore that. So whatever my concentration is, that is also my hydrogen ion concentration. So my H plus concentration is 1.9 times 10 to the negative 10th molar. Okay, so now from here, I want to go to pH. So I am going to do negative log of that number, and that will give me pH. So negative log of 1.9 times 10 to the negative 10th, 9.72. I have two significant figures in the prompt or in my question. So that tells me for pH, I need 2 digits after the decimal. And this is basic. Okay, so you're probably thinking, how can I have a basic pH, because this is above 7, when I have an acid? Okay, this is a tricky one. Picked it on purpose. So everybody that quit watching probably should not have quit watching. Oh well. Anyway, so if you look at this concentration and you think about when we talked about the auto-ionization of water. So we had water plus water, and that was in equilibrium with the hydronium ion and hydroxide. And we learned that Kw, so the ion product of water, 1 times 10 to the negative 14th equals the hydronium ion concentration times the hydroxide ion concentration. If I want to solve for these two, they're basically the same because they both have the same molar coefficient. So I've got 1 times 10 to the negative 14th equal to x squared. So x is equal to 1 times 10 to the negative 7th molar. Okay, now what this means is that the concentration of hydronium is 1 times 10 to the 7th molar, and so is the concentration of hydroxide. Well, if I do the negative log of this number, I am going to get a pH of 7, which would be a neutral solution. So what's happening here is that the hydrogen ion concentration or hydronium ion concentration of water is greater than what we were given in B. So water contributes more hydronium ions than this nitric acid does because it's so dilute. So the pH of that solution is actually 7.